Hello, and welcome to Space for Sleep. The most important matter in the universe may be the matter we cannot see. That is not a poetic exaggeration. It is one of the central facts of modern cosmology. The stars, planets, nebulae, gas clouds, galaxies, dust, black holes, and living things made of atoms are only the visible part of a much larger structure. Ordinary matter, the kind that emits, absorbs, reflects, and scatters light, makes up only a small fraction of the cosmic inventory. A much larger share of the matter in the universe appears to be something else, something that does not shine, does not block light, does not produce spectral lines, and does not seem to interact with electromagnetic radiation in any ordinary way. We call it dark matter. The name sounds simple, almost too simple, as if we are merely saying there is matter in the dark. But the meaning is deeper. Dark matter is not darkness. It is not empty space. It is not dust. It is not cold gas hiding between stars. It is not a black hole population large enough to explain the missing mass. It is, as far as current evidence shows, a form of matter that reveals itself primarily through gravity. It bends light. It shapes galaxies. It holds galaxy clusters together. It gives the cosmic web its scaffolding. It seems to have helped ordinary matter gather into the galaxies where stars, planets, and eventually life could form. And yet no one has ever directly detected a dark matter particle. That is the tension that makes this subject so powerful. For retention, that tension should stay alive in every section. If the script becomes only a list of evidence, the mystery becomes dry. If it becomes only mystery, it loses trust. The strongest version keeps both. The evidence is strong enough that scientists cannot ignore dark matter, but the absence of direct detection keeps the subject open. Every few minutes, the viewer should feel both sides again. We know it is there gravitationally. We do not know what it is physically. That double feeling is the engine of the story. Dark matter is one of the strongest scientific inferences in astronomy, but also one of the deepest unsolved mysteries in physics. We can map where it is. We can measure how much of it the universe contains. We can simulate how it shapes structure across billions of years. We can see its gravitational fingerprints in rotating galaxies, colliding clusters, gravitational lenses, the cosmic microwave background, and the arrangement of galaxies across space. But we still do not know what it is made of. This is not a small gap in knowledge. It is a missing identity for most of the matter in the cosmos. A good way to feel the strangeness is to imagine the Milky Way. The bright disk of stars, gas, dust, and spiral arms is only the visible center of a much larger gravitational structure. Around it extends a dark matter halo, vast and invisible, reaching far beyond the stars we see. The solar system moves through that halo. Earth moves through it. The room you are in moves through it. If the leading particle models are right, dark matter is passing through your body constantly, at high speed, almost never touching anything. That last phrase is important. Almost never. If dark matter interacted strongly with ordinary matter, we would have seen it long ago. It would glow, scatter, collide, slow down, heat gas, or leave obvious laboratory traces. Instead, it behaves like something almost perfectly ghost-like, but not powerless. It does not push on your skin. It does not warm your hand. It does not light up a telescope. But its gravity has helped determine the architecture of the universe. This episode is the story of how scientists came to believe in something invisible, not because they wanted a mystery, but because the visible universe kept moving as if unseen mass were there. We will move from the first hints in galaxy clusters, to Vera Rubin's galaxy rotation curves, to gravitational lensing, the bullet cluster, the cosmic microwave background, modern detector experiments, axions, WIMPs, modified gravity, small-scale puzzles, and the next decade of searches. The central question will remain the same all the way through. what is the universe made of when most of its matter refuses to show itself? The question is simple, but it is large enough to carry the whole episode. It begins in the motion of galaxies and ends in underground laboratories. It begins with telescopes and ends with particle physics. It begins with gravity and ends with identity. That is why dark matter is not just another astronomy topic. It is a bridge between the largest structures in the universe and the smallest possible ingredients of nature. Before the history begins, one wording point matters. Dark matter is sometimes described as an invisible force holding the universe together. That phrase works emotionally, but scientifically dark matter is not a force. It is matter, or at least a gravitating component that behaves like matter. Gravity is the force through which it reveals itself. Dark matter is the hidden mass that gravity is acting from. The distinction matters because it keeps the mystery precise. We are not looking for a new poetic darkness. We are looking for the physical identity of a gravitating substance. The concept of invisible matter affecting the motions of visible objects was not invented by 20th century physicists. This is another reason dark matter is a good subject for a long-com episode. The core reasoning is intuitive. If visible things move as if invisible mass is present, perhaps invisible mass is present. The difficulty is not the first step. The difficulty is the scale of the conclusion. The same reasoning that once revealed a planet now suggests that most matter in the universe belongs to a category we have never touched. The familiar logic leads to an unfamiliar universe. The analogous reasoning, inferring an unseen body from its gravitational effect on observed bodies, had been used to discover Neptune in the 1840s, and the same logic was applied to the stellar dynamics of galaxy clusters in the 1930s by Fritz Zwicky. This analogy is useful, but it also has a limit. Neptune was unseen because it was faint and distant. Once astronomers knew where to look, a telescope could find it. Dark matter is different. It is not simply a planet hiding in the wrong part of the sky. It is not hidden because our telescopes are pointed poorly. It is hidden because it does not seem to use light as ordinary matter does. The Neptune story shows the power of gravity as a clue. The dark matter story shows how strange the clue can become when no visible object appears at the end of it. Zwicky was a Swiss-American astronomer at the California Institute of Technology, a brilliant and difficult man known for his energy, his productivity, his remarkable scientific intuitions, and his pronounced hostility toward colleagues he considered his inferiors, a category that appeared to include most of the astronomical community. In 1933, he published a paper analyzing the velocities of galaxies within the Coma cluster, a rich galaxy cluster containing more than 1,000 galaxies at a distance of about 320 million light-years. Zwicky measured the Doppler shifts of the galaxy's spectral lines, which allowed him to calculate how fast individual galaxies were moving relative to the cluster's average velocity, and found that the velocities were far higher than he expected. The reasoning was this: the Coma cluster is a gravitationally bound system, a collection of galaxies held together by their mutual gravity, orbiting within the cluster's combined gravitational potential. For a gravitationally bound system in equilibrium, the virial theorem relates the total kinetic energy of the system's components to its gravitational potential energy. By measuring the velocities of the galaxies and estimating the cluster's total mass from the light it produces, converting the luminosity of all the galaxies into an estimated mass using reasonable assumptions about the mass-to-light ratio of stellar populations, Zwicky could check whether the system was actually in gravitational equilibrium. It was not. The galaxies were moving far too fast for the visible mass of the cluster to gravitationally confine. If the cluster contained only the mass visible in its galaxies, the velocities Zwicky measured would be too high for the galaxies to remain in a bound cluster. They would fly apart. For the cluster to be stable, there had to be additional, unseen mass providing the gravitational confinement. Zwicky's estimated missing mass was enormously larger than the mass inferred from the visible light, though the exact factor was uncertain because the measurements and mass-to-light estimates were difficult. Zwicky called this missing mass dunkle materie, dark matter, in his 1933 paper. Zwicky's discovery was initially received with limited attention. The measurement was difficult, the uncertainties in mass estimation were substantial, and the astrophysical community was preoccupied with other problems. This slow reception is important. Science does not always respond instantly to a correct idea. Sometimes the measurement is too uncertain. Sometimes the language is unfamiliar. Sometimes the person making the claim is difficult. Sometimes the field lacks the tools to follow the clue. Zwicky saw something important, but the full weight of the missing mass problem required better observations, better instruments, and a different astronomical context. The mystery was visible before the field was ready to reorganize around it. The discovery sat in the literature, acknowledged but not urgently addressed, for several decades. The observations that truly established dark matter as an unavoidable conclusion and brought it to the center of astrophysics were made not in galaxy clusters, but in individual galaxies, and they were made primarily by a woman whose contributions to the field took decades to receive the recognition they deserved. Vera Rubin was a Washington, D.C. native who developed a passion for astronomy as a child, watching stars through her bedroom window, navigated an academic world deeply resistant to women in science through persistence and exceptional ability, and eventually found her scientific focus in the dynamics of spiral galaxies. Working with the astronomer Kent Ford at the Carnegie Institution for Science in Washington from the late 1960s onward, Rubin applied a new generation of spectrographic technology, far more sensitive than anything previously available, to the systematic measurement of how fast stars and gas clouds at different distances from the centers of spiral galaxies were moving. This is a good place to keep the story visual. Imagine a spiral galaxy seen from the side or at an angle. One side of the disk is moving slightly toward us, shifting its spectral lines toward blue. The other side is moving away, shifting them toward red. By measuring those shifts at different distances from the center, astronomers can reconstruct how fast the galaxy is rotating. The galaxy becomes a clock whose hands are made of starlight. Rubin and Ford were reading that clock more carefully than anyone had before. The expected result, from Keplerian physics, was straightforward. In our solar system, planets farther from the Sun orbit more slowly. Mercury, innermost, moves at about 47 kilometers per second, while Neptune, outermost, moves at about 5 kilometers per second. This declining velocity with distance from the central mass is a direct consequence of the inverse square law of gravity. The same pattern should apply to galaxies. Stars and gas clouds in the outer regions of a spiral galaxy, far from the central concentration of mass in the bulge, should orbit more slowly than stars and gas in the inner regions. What Rubin and Ford found, measuring galaxy after galaxy with their spectrograph, was the opposite. The rotation curves, plots of orbital velocity as a function of distance from the galaxy center, were flat. Stars in the outer regions of spiral galaxies were moving at roughly the same velocity as stars in the inner regions, not slower. The rotation velocity did not decline with increasing distance from the center. It stayed approximately constant all the way to the outermost detectable portions of the galaxy. A flat rotation curve has an immediate and unambiguous implication. The implication is simple enough to feel without equations. If the outer stars are moving fast and still remain in orbit, something is providing the gravity needed to hold them. The visible stars and gas are not enough. Either there is more mass than we see, or gravity behaves differently from what we think. Those are the two great paths out of the problem: dark matter or modified gravity. The rest of the episode is, in a sense, the story of why dark matter became the dominant path. By the same Keplerian physics that predicts declining velocity for an isolated central mass, a flat rotation curve implies that the amount of mass enclosed within any given radius increases linearly with that radius. As you go farther from the galaxy's center, you keep finding more mass, not concentrated in any visible structure, but distributed throughout the volume, in a halo surrounding the visible galaxy. The flat rotation curves of spiral galaxies imply that most of the mass of any spiral galaxy is in an extended, invisible halo, far more mass in the halo than in the visible disk, and that this halo mass has a density profile that falls off as approximately the inverse square of distance from the center. Rubin and Ford published their first major paper on spiral galaxy rotation curves in 1970, and the decades following produced more and more galaxies with the same result. The flat rotation curve is not a peculiarity of specific galaxies or special environments. It is a universal feature of spiral galaxies. Across spiral galaxies, the repeated pattern is rotation that stays approximately flat into the outer disk, implying that spiral galaxies are generally embedded in extended dark matter halos. The systematic nature of this result, flat rotation curves across large samples of spiral galaxies, makes the dark matter explanation difficult to evade. It is one thing to claim an anomaly in a specific system might reflect a measurement error or an unusual physical situation. It is another to claim that the same anomaly appears in hundreds of independently studied systems. The universality of flat rotation curves is strong evidence that the missing mass is not an observational artifact or a local peculiarity, but a fundamental feature of galaxy structure. For a viewer, this is where the first real hook lands. The stars at the edge of a galaxy should, by the simplest expectation, move more slowly. They do not. The outer disk keeps turning too fast. The galaxy behaves as if it is embedded in something larger than the visible disk, something that adds gravity without adding light. That image is easy to hold in the mind. A bright spiral galaxy, beautiful and visible, sitting inside a much larger invisible halo. The galaxy we photograph is not the whole galaxy. It is the glowing part of a deeper gravitational body. This is one of the strongest retention points in the episode because it changes how the viewer imagines every galaxy from that moment onward. Vera Rubin died in 2016 without receiving the Nobel Prize, a circumstance that was widely noted as a significant oversight by the Swedish Academy, which has historically awarded the Physics Nobel for discoveries of this magnitude. Her work is now universally recognized as foundational to dark matter astrophysics. Rubin's story also gives the episode a human center. Dark matter can easily become abstract. Curves, spectra, halos, cross-sections, power spectra. Rubin's work reminds the viewer that the mystery was not only uncovered by equations, but by careful measurement, patience, and persistence. The flat rotation curves did not arrive as a single dramatic revelation. They accumulated galaxy by galaxy, night after night, spectrum after spectrum. That slow accumulation is part of the strength of the evidence. The evidence for dark matter extends well beyond galaxy rotation curves. For additional, independent lines of evidence, each derived from completely different physical processes and different observational techniques, converge on the same conclusion. This is the section that turns dark matter from a galaxy problem into a universe problem. If the script stayed only with Rubin's rotation curves, the viewer might think dark matter is a special issue in spiral galaxies. But the evidence is broader and more unsettling. The same missing gravitational component appears when light bends around clusters, when hot gas sits in deep gravitational wells, when the early universe rings with acoustic patterns, and when galaxies form the cosmic web. Each method has different assumptions. Each looks at a different era or scale. Their agreement is why dark matter became the standard explanation. The first is gravitational lensing. Lensing is also one of the best ways to keep the viewer visually engaged. A galaxy cluster can act like a distorted cosmic glass. Background galaxies stretch into arcs. Multiple images of the same source can appear around the lens. Weak lensing can reveal invisible mass statistically across enormous regions of sky. The viewer does not need to see dark matter directly to understand the drama. Light from distant galaxies arrives bent because something massive lies in the way. The invisible leaves fingerprints on the visible. General relativity predicts that mass bends the paths of light rays passing near it, the same prediction that was confirmed by Eddington's eclipse observations in 1919. A massive object between a background source and the observer will deflect the source's light around it, distorting the apparent position and shape of the background object. For very massive objects, galaxy clusters, this lensing effect is dramatic enough to produce multiple images, arcs, and rings of background galaxies distorted around the cluster. For lower mass objects, the lensing is weaker but still measurable as a statistical coherent distortion of background galaxy shapes, a signal called weak gravitational lensing. Both strong and weak lensing provide an independent measurement of the total mass of the lensing object, derived entirely from the light-bending geometry rather than from any assumption about what the mass is made of. This is why gravitational lensing is so powerful. It does not care whether the mass is bright, dark, hot, cold, ordinary, exotic, smooth, clumpy, stellar, gaseous, or invisible. Light follows the curvature of space-time. If the light is bent more strongly than visible matter can explain, then the gravitational field is stronger than the visible matter can provide. In that sense, lensing is one of the cleanest ways the universe tells us where mass is, even when the mass itself refuses to shine. When lensing mass estimates are compared with luminosity-based mass estimates for galaxy clusters, the lensing masses are consistently 5 to 10 times higher than the luminosity-based masses. The extra mass is not visible in any wavelength. It is dark matter, and lensing measures its total amount and its three-dimensional distribution. Weak lensing surveys, measuring the subtle coherent distortions of millions of background galaxy shapes across large areas of the sky, have now been used to construct detailed maps of the dark matter distribution in the universe, showing that dark matter traces the same large-scale cosmic web structure seen in galaxy surveys, with dark matter halos surrounding every galaxy and cluster, connected by dark matter filaments across cosmic scales. Weak lensing is difficult to picture because the effect on any one galaxy is tiny. No single background galaxy shape is enough. Galaxies have their own shapes, orientations, and irregularities. The signal emerges statistically from millions of slight distortions aligned in a coherent way. It is like hearing a pattern in an enormous crowd by averaging many nearly inaudible whispers. That makes weak lensing one of the great achievements of modern survey astronomy, measuring invisible mass not through one dramatic arc, but through the collective bending of light across the sky. The second independent line of evidence comes from X-ray observations of hot gas in galaxy clusters. When galaxy clusters form, the ordinary gas associated with them is heated to very high temperatures, tens of millions to hundreds of millions of Kelvin, by the gravitational compression of the cluster's potential well. This hot gas emits X-ray radiation, detectable by space-based X-ray telescopes like Chandra and XMM Newton. From the temperature and density distribution of the X-ray emitting gas, and from the requirement that the gas be in hydrostatic equilibrium within the cluster's gravitational potential, neither escaping nor collapsing, the total mass of the cluster can be derived independently of the lensing method. This is another kind of weighing. The hot gas in a cluster is not a small side detail. It can contain more ordinary matter than the stars in the cluster's galaxies. It glows in X-rays because it is extraordinarily hot, heated by the deep gravitational well of the cluster. If the well were shallow, the gas would not have the temperature and pressure structure observed. If the well is deep, there must be more mass. Again, the visible matter asks for invisible gravity. These X-ray mass estimates agree with the lensing estimates, and both exceed the mass in visible stars and galaxies by the same large factor, confirming that most of the cluster mass is dark. The third line of evidence comes from the cosmic microwave background, the ancient light that was released when the universe first became transparent, about 380,000 years after the Big Bang. The cosmic microwave background also gives the episode a change of scale. Until this point, the evidence has been galaxies and clusters, enormous, but still objects. The CMB is the entire young universe. It is a wall of ancient light surrounding us in every direction, carrying the imprint of sound waves, density fluctuations, and the balance of ingredients in the early cosmos. Dark matter is not only something we infer around galaxies. It is part of the recipe of the universe from near the beginning. The tiny temperature fluctuations in the CMB encode information about the distribution of matter in the early universe, and the specific pattern of these fluctuations depends sensitively on the relative amounts of ordinary matter, dark matter, and radiation in the early universe. The CMB is sometimes called a baby picture of the universe, but it is more than an image. It is a precision instrument left behind by the early cosmos. The peaks and valleys in its power spectrum are like notes in a cosmic chord. Change the amount of ordinary matter, and the notes shift. Change the amount of dark matter, and the pattern changes again. The observed pattern fits a universe with much more dark matter than ordinary matter. This is one of the most elegant arguments because it reaches back before galaxies existed. Dark matter was needed before spiral galaxies had disks to rotate. The CMB power spectrum, the mathematical characterization of how temperature fluctuations are distributed across different angular scales, can only be reproduced by detailed calculations if dark matter exists in the universe in approximately the right amount. Fitting the CMB without dark matter requires modifying the physics of the early universe in ways that conflict with other observations. The CMB tells us not only that dark matter exists, but how much of it there is, approximately 5 times the amount of ordinary matter by mass. This is a different kind of evidence from galaxy rotation. A rotation curve is local and late in cosmic history. It tells us about a galaxy after billions of years of evolution. The cosmic microwave background is ancient. It tells us about the universe when it was only about 380,000 years old. The fact that dark matter appears in both stories, in young universe light and in modern galaxies, is one of the reasons it is so hard to replace with a simple local explanation. Dark matter is not only a patch for spiral galaxies. It is written into the early universe. The fourth line of evidence comes from the large-scale structure of the universe, the distribution of galaxies across cosmic scales, and the way that distribution has evolved from the early universe to the present. Large-scale structure turns dark matter from a missing mass problem into a cosmic architecture problem. A galaxy rotation curve tells us something is wrong with one galaxy's visible mass. A cluster tells us the same problem exists on larger scales. But the cosmic web tells us that dark matter is not merely tucked into objects. It is part of the pattern of the universe itself. It determines where clusters form, where filaments stretch, where voids open, and where ordinary matter had the chance to cool into galaxies. The universe is not sprinkled randomly with light. It is organized. The seeds of cosmic structure, the tiny density fluctuations visible in the CMB, grew under gravity over cosmic time, with slightly overdense regions attracting more material and eventually collapsing into galaxies and galaxy clusters. The details of how this structure grew, the characteristic clustering scales, the galaxy power spectrum, the abundance of galaxy clusters as a function of mass and redshift, depend on the properties of the dark matter. Cold dark matter particles moving slowly relative to the speed of light at the time of structure formation, predicts a specific pattern of hierarchical structure growth that matches the observed large-scale structure of the universe with remarkable accuracy, at scales from individual galaxies to the cosmic web. The word cold here does not mean cold in the everyday sense. It means the dark matter was moving slowly enough in the early universe that small structures could survive and grow. Hot dark matter, moving close to the speed of light, would smear out small-scale structure and produce a universe unlike the one we observe. Cold dark matter allows small halos to form first, then merge into larger structures. This hierarchical growth matches the way galaxies and clusters appear to have assembled over cosmic time. The temperature word is really a structure word. All four of these independent lines of evidence, rotation curves and velocity dispersions, gravitational lensing, X-ray gas physics, and CMB and large-scale structure, point to the same conclusion and yield consistent quantitative estimates of how much dark matter there is. Approximately 27% of the universe's total energy content, compared to about 5% for ordinary matter. The convergence of these different methods using completely different physical processes is the most powerful argument for dark matter's reality. This convergence is the point where the story becomes difficult to dismiss. If dark matter were needed only to explain one galaxy, it might be a mistake. If it were needed only for one cluster, it might be a special case. If it appeared only in one kind of telescope data, it might be an instrumental bias. But the same missing gravitational component appears in galaxy rotation, cluster motion, lensing maps, hot gas physics, the cosmic microwave background, and the growth of the cosmic web. The evidence does not come from one door. It comes from many doors opening into the same dark room. This line is the turning point. After this, the viewer no longer has to wonder whether dark matter is just an old hypothesis from galaxy rotation curves. The mystery has become a convergence. The question changes from, why do astronomers believe this, to how can something with so much evidence still have no known identity? That second question is stronger. It is what carries the middle of the script. What is dark matter made of? This is the question that direct and indirect detection experiments have been attempting to answer for decades, and it remains unanswered. This is the hinge of the episode. Before this point, the listener has heard why astronomers believe dark matter is there. After this point, the question becomes why physicists still cannot catch it. That shift should feel dramatic. The universe has provided a gravitational map, but not a particle label. It is like knowing the outline of a continent from its effect on ocean currents, without ever seeing the land itself. At this point, the story changes from astronomy to particle physics. The first half of the mystery is gravitational. Galaxies rotate too fast, clusters hold together too strongly, light bends too much. The cosmic microwave background contains the wrong pattern unless invisible matter is included. The second half is microscopic. What particle or object could produce those gravitational effects while staying hidden from light? This turn is important for keeping the viewer with us. The question is no longer only where the missing mass is. The question becomes what kind of reality can be so massive on cosmic scales and so silent in a laboratory. The most extensively studied dark matter candidate for the past several decades has been the weakly interacting massive particle, or WIMP. A WIMP is a hypothetical particle with a mass roughly in the range of 1 to 1,000 times the proton's mass, interacting with ordinary matter through the weak nuclear force and gravity, but not through electromagnetism. WIMPs are attractive as dark matter candidates for several reasons. The WIMP was attractive because it promised a clean ending. If dark matter were a new particle connected to the weak nuclear force, then the same physics that explains processes inside atoms and particle accelerators might also explain the mass of galaxies. The missing matter in the sky and the missing particle in the laboratory would become one discovery. It would be elegant, cosmology and particle physics meeting in a single particle. That elegance is why the WIMP dominated the imagination of dark matter searches for so long. The most compelling is the WIMP miracle. The word miracle should be understood carefully. Physicists did not mean a supernatural event. They meant a surprising numerical coincidence. A particle with roughly weak scale interactions could naturally freeze out in the early universe with about the right abundance to explain dark matter today. That coincidence made the WIMP feel less like an arbitrary guess and more like a clue. For years, this gave the dark matter search a strong narrative direction. Build better detectors, search deeper, and the particle might appear. In the very early universe, when temperatures were extraordinarily high, all types of particles, both known and hypothetical, were in thermal equilibrium, continuously being created and destroyed. As the universe expanded and cooled, specific particle types froze out of thermal equilibrium when the temperature dropped below the threshold for their creation, after which they survived as relics. The calculation of how many WIMP relics would survive from the early universe, their relic abundance, depends on their mass and the strength of their interactions. For a particle with mass in the 10 to 1000 gigaelectronvolt range interacting through something like the weak force, the relic abundance comes out to approximately the observed dark matter abundance. This coincidence, that a particle of the right mass and coupling strength to be predicted by electroweak physics independently turns out to have a relic abundance matching the observed dark matter density, seems too good to be accidental, and it motivated the WIMP paradigm. WIMPs are also motivated by supersymmetry, the theoretical framework that predicts a partner particle for every particle in the Standard Model, with the lightest supersymmetric particle, LSP, being stable and, in many models, being a WIMP. The absence of supersymmetric particles at the Large Hadron Collider, where energy scales sufficient to produce them were expected to reveal them, has significantly constrained supersymmetric models, though not ruled out all WIMP scenarios. The Large Hadron Collider changed the mood of the field. It did not disprove dark matter. It did not even disprove all supersymmetry. But it removed many of the simplest hopes that new weak-scale particles would appear quickly once the machine reached high energy. The universe did not hand over the missing particle in the first obvious place. This is a recurring pattern in fundamental physics. Nature often gives hints before it gives identities. The neutrino was proposed before it was detected. Gravitational waves were predicted long before they were measured directly. The Higgs boson was part of the theoretical structure for decades before the LHC found it. Dark matter may be following the same path, but on a longer and more difficult road. The difference is that the gravitational evidence for dark matter is already written across the sky. That pushed dark matter research into a broader, more cautious era. The experimental search for WIMPs has been one of the most active areas in fundamental physics for 3 decades. The concept behind direct detection is straightforward. If WIMPs are distributed in a halo surrounding our galaxy, they should be streaming through the solar system continuously at approximately 200 to 300 kilometers per second. There is a seasonal detail that makes the search even more elegant. Because Earth orbits the Sun while the Sun moves through the galaxy, the relative speed between Earth and the dark matter halo should change slightly during the year. In some models, this produces an annual modulation in the expected detection rate, a small rise and fall as Earth's motion aligns more or less with the solar system's motion through the halo. Experiments have looked for this modulation, because a signal that changes with the right yearly rhythm would be harder to confuse with many ordinary backgrounds. The idea is beautiful, the planet's orbit becoming part of a dark matter detector. Occasionally, rarely, but measurably if the detector is large enough and sensitive enough, a WIMP should collide with an atomic nucleus in a detector, transferring a small amount of energy to the nucleus and causing it to recoil. This nuclear recoil, typically carrying an energy of only a few to tens of kiloelectronvolts, can be detected by appropriate instruments as a tiny pulse of heat, light, or ionization. The challenge is that the expected signal is extraordinarily rare, perhaps one event per year per ton of detector material, and background noise from cosmic rays, radioactive decay of detector components, and neutrinos produces vastly more events than any WIMP signal. This gives underground detectors an unusual emotional quality. They are not dramatic machines from the outside. They sit deep under rock, quiet, shielded, cold, or ultra-pure, waiting for something that may not happen even once in a year. A detector can be an enormous instrument built to notice a tiny recoil, one nucleus nudged by one invisible particle. The experiment is almost the opposite of a telescope image. Instead of collecting light from billions of stars, it waits for the faintest possible touch. That quiet waiting fits the subject. Dark matter is everywhere, but almost never speaks. The approach is therefore to place the detectors deep underground, where the rock overhead filters out cosmic ray particles, to use detector materials with very low natural radioactivity, to build the detectors from the purest materials possible, and to use the specific signatures of WIMP recoils to distinguish them from background events. The progression of WIMP direct detection experiments over the past 30 years has been a continuous drive to lower backgrounds and larger detector masses. The CDMS experiments at the Sudan Mine and Stanford Underground Research Facility used germanium and silicon detectors cooled to millikelvin temperatures. The xenon experiments at the Gran Sasso Laboratory in Italy used liquid xenon, which efficiently records both the ionization and scintillation light produced by a nuclear recoil, allowing discrimination between the recoil signatures of WIMPs and those of background electron recoils. The LUX experiment at the Sanford Underground Research Facility in South Dakota used the same liquid xenon technology. The Panda X experiments in China, the DEAP experiment in Canada, and the current generation LZ experiment, also using liquid xenon, now at several tons, each improved upon the previous generation's sensitivity. By the mid-2020s, the situation had become even sharper. The leading liquid xenon experiments, LZ, Xenon NT, and Panda X4T, had pushed WIMP searches into territory far beyond the expectations of many early models. LZ, using a large exposure collected between 2023 and 2025, continued to report no significant excess attributable to dark matter, while setting some of the strongest limits on WIMP interactions. At the same time, LZ reported a solar neutrino signal from boron-8 neutrinos, the kind of background that can begin to resemble the faint nuclear recoils expected from some dark matter models. That is both a success and a warning. The experiments are becoming sensitive enough to hear the universe's neutrino whisper, but the dark matter signal has still not appeared. This does not kill the WIMP idea, but it changes its emotional status. The WIMP is no longer the easy miracle waiting just beyond the previous detector. It is a candidate under pressure. Pressure is not the same as death. This is important for tone. The script should not declare a candidate finished simply because it has not appeared yet. Physics has many examples of particles and signals found after long searches. But the emotional story has changed. The WIMP once felt almost expected. Now it feels like one possibility among many, forced into narrower and more carefully defined regions of parameter space. The result of all this effort has been a steady tightening of the constraints on WIMP properties, the combination of mass and interaction cross-section that would be compatible with both the observed dark matter density and the absence of a detected signal. Current limits exclude WIMPs with interaction cross-sections far below what early models predicted as natural, and the most straightforward versions of the WIMP miracle have been significantly constrained. The WIMP has not been found. The absence of detection after decades of searching is scientifically significant but not yet definitive. The WIMP parameter space is large, and many versions of WIMP models remain compatible with all experimental constraints. That phrase, parameter space, can sound dry, but it is central to how the search works. A WIMP is not one exact particle. It is a broad family of possibilities with different masses and interaction strengths. An experiment excludes a region of that map. Another experiment excludes a different region. Over time, the map of what remains possible shrinks. The absence of detection is therefore not empty information. It redraws the territory. Dark matter research advances through exclusions as well as discoveries. The current frontier experiments, LZ, Xenon NT, Panda X4T, are probing sensitivity levels only recently achievable and plan next-generation experiments with 10 to 50 tons of liquid xenon will push further still. A specific floor exists, the neutrino floor or neutrino fog, below which atmospheric and astrophysical neutrinos produce backgrounds indistinguishable from WIMP signals without enhanced directional sensitivity. The neutrino fog is important because it shows the field entering a new era. Neutrinos are real particles from the sun, the atmosphere, supernovae, and other cosmic sources. They interact weakly, just as WIMPs were expected to interact weakly. As detectors become more sensitive, neutrino events become an unavoidable background. In one sense, that is a triumph. The experiments are reaching sensitivity levels where even neutrinos, once nearly impossible to detect, become part of the noise. In another sense, it means the easy search space is shrinking. The silence is becoming more informative. Future experiments capable of determining the direction of nuclear recoils are being developed to push sensitivity below this floor, but they represent a technical challenge beyond current capabilities. The honest assessment is that the simplest and most theoretically motivated WIMP models are under increasing pressure from experimental constraints, while the overall WIMP parameter space remains viable. This is a careful sentence, but an important one. It avoids two mistakes. The first mistake is saying WIMPs are dead, which is too strong. The second is pretending nothing has changed, which is too weak. The best version of the story is honest. The WIMP remains possible, but the easy, elegant versions have become harder to defend. The silence of detectors now carries real theoretical weight. A good mystery evolves as evidence accumulates. This is where the mystery becomes more interesting rather than less. A simple story would be satisfying. Astronomers infer dark matter, particle physicists predict the right particle, underground detectors find it, and the missing mass problem closes neatly. But that is not what happened. The detectors became better. The backgrounds became lower. The exposure increased. The silence continued. In a weak script, this would feel like failure. In a strong script, it becomes the second hook. The universe is giving us gravitational evidence, but refusing to give us the particle. The next decade of direct detection experiments will either find something, in which case a revolution in fundamental physics has occurred, or will push the constraints further into territory where the simplest WIMP models are no longer viable, narrowing the possibilities and motivating further theoretical refinement. Beyond the WIMP, a wide range of alternative dark matter candidates has been proposed and is being actively studied. This expansion of candidates is not a sign of chaos. It is a sign that the dark matter problem touches many parts of physics. If the missing mass is not a simple WIMP, It may live in an axion field, a sterile neutrino sector, a self-interacting dark sector, primordial black holes, or something not yet named. Each candidate is constrained by cosmology, astrophysics, laboratory experiments, and particle theory. The search is widened because the mystery deserves more than one net. This widening also helps keep the script from becoming repetitive. Instead of one detector failing again and again, the viewer sees a changing landscape of ideas. Heavy particles, light fields, sterile neutrinos, hidden forces, primordial black holes, modified gravity, dwarf galaxies, lensing surveys. The mystery remains the same, but each candidate reveals a different possible universe. That variety is important for retention because every section opens a new door. The axion is perhaps the most theoretically compelling alternative. The axion was proposed in 1977 by Roberto Pecchiai and Helen Quinn as a solution to a specific problem in particle physics called the strong CP problem, a puzzle about why the strong nuclear force appears to preserve a symmetry, CP symmetry, combining charge conjugation and parity, that there is no fundamental reason for it to respect. The axion has a different emotional appeal from the WIMP. The WIMP was attractive because it came from a broad expectation that new weak-scale physics might exist. The axion is attractive because it was invented to solve a completely different problem, and then turned out to be a possible dark matter candidate. That makes it feel less like a particle invented only to fill a cosmological hole, and more like a particle that could connect two independent mysteries. If WIMPs were the obvious suspect for decades, axions are the elegant suspect waiting in another room. The Pecchiai-Quinn mechanism and the axion it predicts elegantly solves this problem, and the axion has the additional virtue that it is cosmologically produced in the right abundance to be all or much of the dark matter if it has a mass in a specific range, roughly 1 microelectronvolt to 1 millielectronvolt, far lighter than any WIMP scenario. An axion with a mass in this range is an extraordinarily light particle, about 10 to the minus 12 times the mass of the electron, and it is almost impossible to detect through the interactions that reveal conventional particles. But axions can interact with photons in the presence of a strong magnetic field, converting between axion and photon through the Primakov effect. This conversion, axion in, photon out, or vice versa, is the basis of dedicated axion search experiments. The ADMX experiment in the United States and the Haystack experiment use high-Q microwave cavities in strong magnetic fields, tuning the cavity resonance frequency to match the expected axion photon conversion frequency, and searching for tiny signals of photon power produced by axion conversion. The Abracadabra experiment uses a different geometry, and the CAPP experiment in South Korea represents a major international axion search program. The challenge is that the axion's coupling to photons is extraordinarily weak. The conversion probability in realistic laboratory-scale magnetic fields is tiny, requiring very high magnetic field strengths, very large detector volumes, very long integration times, and extremely sensitive microwave receiver technology. The current experiments are beginning to probe the range of axion masses and couplings predicted by the simplest models, and significant improvements in sensitivity over the next decade are anticipated. Axion searches also show how different dark matter can be from ordinary intuition. A detector might not be waiting for a particle to slam into a nucleus. It might be waiting for a field to convert into a photon inside a magnetic field. The signal may be a tiny excess of microwave power, not a flash, not a track, not a collision. The search therefore requires different technology, different patience, and a different mental image of what matter can be. The word matter does not necessarily mean little hard grains flying through space. No axion has yet been detected. Still, the axion search has an advantage for storytelling. It gives dark matter a sound-like quality. Axion experiments often tune through possible frequencies, because an axion converting into a photon would produce a signal related to its mass. The experiment listens, in a sense, through an invisible radio dial of possible dark matter masses. Most of the dial is silent. Somewhere, perhaps, there could be a faint excess at the right frequency. This image, tuning a detector through the dark, is a powerful way to keep the viewer engaged. Ultralight axion-like particles, sometimes called fuzzy dark matter, represent an extension of the axion scenario to much lighter masses, down to roughly 10 to the minus 22 electron volts. Fuzzy dark matter changes the image of what a particle can be. A WIMP feels like a tiny bullet passing through a detector. An axion feels like a whisper in a magnetic field. Fuzzy dark matter feels almost like a cosmic wave, because at such tiny masses the particle's quantum wavelength becomes astrophysically large. It is still matter in the equations, but its behavior can smooth structures on the scale of dwarf galaxies. This is why dark matter candidates are not just different names. They produce different universes at small scales. At such extremely low masses, the de Broglie wavelength of the dark matter particle becomes macroscopically large, kiloparsecs, which causes quantum wave effects to manifest at astrophysical scales. Fuzzy dark matter forms smooth cores in the centers of galaxies rather than the cuspy density profiles predicted by cold dark matter, potentially explaining observed discrepancies between the density profiles of the smallest galaxies and the predictions of pure cold dark matter simulations. The observational tests of fuzzy dark matter include the distribution of matter in dwarf galaxies, the properties of Lyman alpha forest absorption in quasar spectra, and the detailed power spectrum of density fluctuations at small scales. Sterile neutrinos, hypothetical partners to the three known neutrino types, but unlike them not participating in weak interactions, represent another class of viable dark matter candidates. Sterile neutrinos are compelling partly because ordinary neutrinos already taught physics a lesson in humility. For a long time, neutrinos were assumed to be massless in the simplest standard model picture. Then neutrino oscillations showed that they have mass. They are already ghostly, weakly interacting particles passing through matter almost unnoticed. A sterile neutrino would be even more hidden, a neutral particle outside the weak interaction, detectable mainly through mixing, decay, or cosmological effects. Again, the theme repeats. Dark matter candidates are not random inventions. They often grow from real cracks or extensions in known physics. A sterile neutrino in the keV mass range would be produced in the early universe through neutrino oscillations and could constitute some or all of the dark matter. It would decay very slowly into a lighter active neutrino and an X-ray photon, producing a potentially detectable line signal in X-ray observations of galaxy clusters and dwarf galaxies. An anomalous X-ray line at about 3.5 keV was detected in observations of the Perseus galaxy cluster and several other systems by the XM Newton and Chandra X-ray telescopes in 2014, and the possibility that it represents a sterile neutrino decay signal generated significant interest. Subsequent observations with more sensitive instruments, particularly the Hitomi X-ray satellite in its brief operational period before a technical malfunction ended the mission, did not confirm the line with the significance that would establish it as real. The interpretation of the 3.5 kiloelectron-volt feature remains controversial and unconfirmed. The cautious view is that it cannot be treated as evidence for dark matter unless future observations establish the line and rule out ordinary astrophysical or instrumental explanations. Self-interacting dark matter that interacts with itself through a new force beyond gravity, while still not interacting electromagnetically with ordinary matter, has been proposed to address discrepancies between the predictions of pure cold dark matter simulations and observations of the internal structure of galaxies and clusters. Self-interacting dark matter asks a subtle question. What if dark matter is dark to us, but not completely dark to itself? It might not scatter light. It might not collide with atoms. But perhaps dark matter particles can bump into one another through a hidden force. If so, dark matter halos would not be perfectly collisionless. They could exchange energy internally, smoothing dense centers and changing the structure of small galaxies. This idea keeps the gravitational success of dark matter while opening the possibility that the dark sector has its own physics. Pure cold dark matter predicts that the density of dark matter in the centers of dwarf galaxies should be cuspy, steeply rising toward the center, and that clusters should have specific density profiles in their inner regions. Observations of some dwarf galaxies suggest shallower central density profiles, cores rather than cusps, and some cluster cores appear less concentrated than pure cold dark matter predicts. Self-interactions between dark matter particles, with a cross-section comparable to that of nuclear scattering, could transport energy in the dark matter fluid in ways that smooth out the central density, producing cores. The bullet cluster provides constraints on the self-interaction cross-section, because the dark matter halos of the two clusters were able to pass through each other apparently without significant interaction, setting an upper limit on how strongly dark matter can self-interact. Primordial black holes, as discussed in the Black Holes and Universe episodes, were proposed as a possible dark matter candidate even before detailed particle physics models were developed. Primordial black holes have a different appeal because they require no new particle. A black hole is a known consequence of general relativity. If black holes formed in the early universe before stars existed, they could be dark, massive, and hard to see. That sounds attractive. But the universe gives many ways to test compact dark objects. Microlensing, gravitational waves, the cosmic microwave background, stellar dynamics, and the survival of wide binary systems and star clusters. Those tests have closed much of the parameter space. The idea is not dead, but it is much more constrained than it once was. If a significant number of small black holes formed in the very early universe from density fluctuations before any stars existed, they could contribute to the dark matter density today. Current constraints, from the absence of microlensing events in searches for compact objects in the Milky Way halo, from the properties of the CMB, from the observed population of binary black holes detected by gravitational wave observatories, and from other probes, have ruled out primordial black holes as the dominant dark matter component across most of the mass range from small fractions of a gram to about 100 solar masses. Some windows remain open, particularly around asteroid mass primordial black holes in the range of approximately 10 to the 15 to 10 to the 20 grams, where direct constraints are currently limited. This is a good example of how dark matter science often works. A candidate is proposed. Then every possible consequence is searched for. If it would bend light in a certain way, microlensing surveys look for that. If it would heat gas, distort the CMB, produce gravitational waves, disrupt stars, or change galaxy evolution, those effects are tested. The candidate is not simply believed or rejected. It is slowly surrounded by constraints. The mystery survives, but it has less room to hide. That is how an unsolved problem can still make progress. The public often imagines science as a sequence of discoveries, but many fields move by elimination. This mass range is excluded. This interaction strength is too large. This candidate cannot make up all of the dark matter. This model conflicts with the CMB. This alternative fails in clusters. The unknown becomes smaller and more sharply outlined. A mystery with boundaries is different from pure ignorance. Boundaries are progress. We may not know what dark matter is, but we know many things it cannot easily be. It cannot be mostly ordinary faint stars. It cannot be only cold gas. It cannot interact electromagnetically like atoms. It cannot be made of primordial black holes across most mass ranges. It cannot have strong self-interactions beyond observed limits. It cannot be absent from the early universe without breaking the CMB and structure formation. The unknown is not infinite. It is being carved into shape, and the carving is happening from both ends. Astronomers carve from the large scale inward, mapping halos, clusters, filaments, dwarf galaxies, and gravitational lenses. Particle physicists carve from the small scale outward, testing masses, cross-sections, couplings, decay channels, and hidden sectors. Somewhere between those approaches, the identity of dark matter must fit. It must explain the sky and survive the laboratory. That is a hard demand. It is also what will make the answer powerful when it comes. The bullet cluster is worth discussing in some depth because it represents the most direct and visually compelling evidence for dark matter as a physically distinct component of the universe, separate from ordinary matter, and because it specifically challenges some of the alternatives to dark matter as theoretical explanations. The bullet cluster, formerly known as 1E0657-558, is the result of a high-velocity collision between two galaxy clusters that occurred approximately 150 million years ago. The bullet cluster deserves time because it gives the episode its clearest visual proof. A viewer can imagine two clusters passing through one another. The galaxies, mostly empty space, continue. The hot gas, spread through the cluster, collides and slows. The dark matter, if it is collisionless, continues with the galaxies. Then astronomers make two maps, an X-ray map of the gas and a lensing map of the mass. The maps do not line up. That mismatch is the story. It is one of the moments where dark matter stops feeling like an accounting trick and starts feeling like a separate component of reality. A cluster collision is slow only by human standards. The galaxies are separated by enormous distances, so most of them pass through without direct collisions. But the hot gas is diffuse and collisional. It feels pressure. It shocks. It heats. It slows. The dark matter, if it interacts only weakly or not at all except through gravity, behaves more like the galaxies than like the gas. It does not stop in the middle. That different behavior is exactly what makes the system useful. The reason this matters is simple. A collision sorts the components. In an undisturbed galaxy cluster, ordinary matter and dark matter may overlap too closely for the eye to separate them. Stars, galaxies, gas, and dark matter all sit in the same broad gravitational structure. But when two clusters collide, the components behave differently. The gas hits gas. The galaxies mostly miss one another. The dark matter, if it is collisionless, should pass through almost like the galaxies. A collision, therefore, becomes a natural experiment. It asks the universe to separate what is usually mixed. The two clusters, each containing hundreds of galaxies and large amounts of hot gas and dark matter, pass through each other at approximately 3,500 kilometers per second. When they collided, the different components of each cluster responded differently to the encounter. The galaxies in each cluster, like stars in a stellar collision, effectively point like relative to the spaces between them, pass through each other without significant interaction, their individual sizes and separations being so large relative to the scale of individual galaxies that actual galaxy-galaxy collisions were rare. The two galaxy populations pass through each other essentially freely, continuing their trajectories. The hot gas, by contrast, is not effectively collisionless. The intergalactic gas in each cluster collided with the gas from the other cluster, creating a massive shock and dramatically slowing the gas. The gas from both clusters piled up near the center of the collision region, displaced from the trajectories of the galaxies. The distinctive bullet-shaped bow shock visible in Chandra X-ray images of the cluster is the compressed, shocked gas from the collision, glowing brilliantly in X-rays at the interface between the two clusters. If the cluster mass were composed primarily of ordinary matter, stars, gas, and compact objects all of the same type, then the collision should have slowed the mass in the same way it slowed the gas, leaving the mass concentrated near the gas. But gravitational lensing mass maps of the bullet cluster, constructed by analyzing the distortions of thousands of background galaxy shapes, show the mass in a very different distribution from the gas. The mass, revealed by lensing, is concentrated in two clumps, one associated with each subcluster's galaxy population, separated from the gas clump between them. The mass passed through like the galaxies, not like the gas. That separation is the key image. The X-ray map says, here is the ordinary hot gas. The lensing map says, here is most of the mass. They are not in the same place. The visible gas, which contains most of the ordinary matter in the cluster, has been slowed by collision. The gravitational mass has moved ahead with the galaxies. This is why the bullet cluster is so compelling even for non-specialists. It turns an invisible inference into a spatial separation you can describe in one sentence. The gravity is not where the ordinary matter is. This is exactly what dark matter predicts. The power of this example is that it separates two questions people often confuse. One question is whether gravity behaves differently from what we think. Another is whether there is unseen mass. In the bullet cluster, the gravitational lensing signal is displaced from most of the ordinary matter. A simple modification of gravity tied only to ordinary matter has difficulty explaining why the gravitational field is centered elsewhere. Dark matter provides a natural answer. Most of the mass is in a collisionless component that moved through the collision. That does not end every debate, but it makes the dark matter explanation much harder to avoid. Dark matter, collisionless, not interacting electromagnetically, would behave like the galaxies, passing through the collision without slowing significantly. The gas, interacting electromagnetically, experiencing pressure and friction, would pile up in the collision region. The result is the spatial separation between the mass, traced by lensing, and the gas, traced by X-rays, that the bullet cluster shows. The separation is a direct demonstration that most of the cluster's mass is not in the gas and not made of the same material as the gas. It is a collisionless, electromagnetically non-interacting component, dark matter. The bullet cluster has been described as the most convincing direct evidence for the existence of dark matter, and it is specifically challenging for the most serious alternative theoretical framework, modified Newtonian dynamics, or MOND. The bullet cluster is not the only merging cluster system used in this way. Other cluster collisions also show separations between gas and gravitational mass, though not always as famously or as cleanly. This matters because a single spectacular object could always be questioned as unusual. A class of systems showing the same general behavior strengthens the case. Colliding clusters are messy, but their messiness is useful. They let the different components of the universe respond in different ways. When nature performs a collision experiment, cosmologists pay attention. The bullet cluster works so well as a story because it gives the invisible a location. In ordinary galaxy rotation curves, dark matter is inferred from motion. In the cosmic microwave background, it is inferred from a pattern in ancient light. In large-scale structure, it is inferred from growth across cosmic time. But in the bullet cluster, the visible gas and the gravitational mass separate on the sky. The ordinary matter slows and heats. The invisible mass keeps going. It is not a photograph of a dark matter particle, but it is a map of where the missing gravity is. A map is not the same as an identification. This distinction is crucial. Astronomers can map dark matter by lensing. They can estimate its density in halos. They can model its role in cosmic structure. But mapping where something is does not tell you what it is. A footprint tells you that something walked there. It does not tell you the creature's full biology. Dark matter has left footprints everywhere. The creature has not been seen. Modified Newtonian dynamics was proposed in 1983 by the Israeli physicist Mordechai Milgram as an alternative explanation for galaxy rotation curves that doesn't require dark matter. Mond enters the story because a responsible dark matter episode should not pretend there is no alternative. The original motivation was simple and clever. Maybe the problem is not missing matter, but the law of motion at extremely low accelerations. Galaxy outskirts are low acceleration environments. If gravity or inertia behaves differently there, the flat rotation curves might be explained without halos of invisible matter. This is a serious idea because it makes risky predictions, and some of those predictions work surprisingly well for galaxies. The basic idea is that Newton's law of gravity, and hence the equations of motion that predict how fast things orbit, is modified at very low accelerations, specifically at accelerations below about 1.2 times 10 to the minus 10 meters per second squared. At this low acceleration threshold, gravity falls off more slowly with distance than the standard inverse square law, maintaining the flat rotation curves observed in galaxy outskirts without requiring any dark matter. The Mond proposal was phenomenologically successful in a way that genuinely impressed even skeptics. This success matters for another reason. It tells us that dark matter halos are not arbitrary. If dark matter exists, its distribution around galaxies is somehow tightly related to the distribution of ordinary matter. Galaxies are messy systems full of gas cooling, star formation, supernovae, black holes, magnetic fields, and feedback. Yet the relationship between visible matter and rotation is often surprisingly regular. That regularity may be a clue to how galaxies settle into equilibrium. So even if Mond is not the final theory, it may still be pointing at something real. That sentence deserves emphasis. Mond is not a fringe idea in the sense of being careless or meaningless. It captured something real about galaxy rotation curves. It explained why the observed acceleration in galaxies correlates so tightly with the acceleration predicted from visible matter alone. Any honest dark matter story has to admit that galaxy dynamics contain regularities that are surprisingly tight. The hard part is not explaining one galaxy. The hard part is explaining galaxies, clusters, lensing, the bullet cluster, the CMB, and the cosmic web together. Milgram's simple formula, with a single free parameter, the acceleration threshold, correctly reproduced the rotation curves of a wide variety of spiral galaxies. More impressively, Mond made specific predictions about the relationship between the distribution of visible matter in a galaxy and its rotation curve, predictions that a dark matter theory would not naturally make, because the dark matter halo distribution is in principle independent of the visible matter distribution. The baryonic Tully-Fisher relation, a tight empirical relationship between the total ordinary mass of a galaxy and its asymptotic rotation velocity, is a natural prediction of Mond, but requires an explanation in dark matter models. The radial acceleration relation, the correlation between the measured centripetal acceleration of stars and galaxies and the acceleration that would be predicted from the visible matter alone, is another tight empirical result that Mond predicts naturally, but that dark matter theories reproduce only with additional assumptions about how dark matter halos adjust to the distribution of ordinary matter. Mond's successes at the scale of individual galaxies are genuine and scientifically important. They are not dismissed by serious physicists and astronomers, but are taken as empirical regularities that any successful theory of dark matter must explain, either through Mond itself being correct or through a deep connection between the dark matter distribution and the ordinary matter distribution that produces Mond-like phenomenology in galaxy dynamics. But Mond encounters severe difficulties at scales beyond individual galaxies. and these difficulties are not easily resolved. At the scale of galaxy clusters, MOND does not eliminate the need for additional mass. The velocity dispersions of galaxies and clusters are too high to be explained by MOND applied to the visible mass of the cluster's galaxies. Even with the modified gravity, there is still a factor of several missing in the mass. MOND advocates have proposed that an additional invisible component, sometimes discussed historically in terms of massive neutrinos, or in later models as sterile neutrino-like matter, might help provide the missing mass in clusters. But ordinary active neutrinos with masses in the few electron-volt range are now strongly constrained by laboratory and cosmological measurements, and adding an invisible mass component reduces the original appeal of MOND as a no-dark matter alternative. The bullet cluster is a more serious problem for MOND. The separation between the mass distribution, traced by lensing, and the gas distribution, traced by X-rays, in the bullet cluster, with the mass following the collisionless galaxies rather than the collisional gas, is difficult to explain without dark matter. MOND, combined with massive neutrinos as the cluster mass component, has been invoked to address this, but the required neutrino distribution needs specific assumptions to match the observations. At the cosmological scale, the CMB power spectrum, the large-scale structure of the universe, the formation of cosmic structure from primordial fluctuations, MOND in its original form makes predictions that are in conflict with observations. Cosmology is where the pressure becomes strongest. A theory of gravity must do more than fit rotation curves. It must explain the acoustic peaks of the CMB, the growth of structure, lensing by clusters, gravitational waves, galaxy cluster masses, and the expansion history of the universe. Dark matter does not solve every detail perfectly, but it fits the broad cosmological evidence in one coherent framework. MOND-like theories have to work much harder to cover the same territory. That is why most cosmologists keep dark matter, even while taking MOND's galaxy-scale successes seriously. A relativistic extension of MOND, called tensor vector scalar gravity, or TeVS, proposed by Jacob Bekenstein in 2004, is capable of reproducing some cosmological observations, but it predicts a CMB power spectrum that differs from the observations in ways that are difficult to reconcile. More recently, various relativistic MOND theories and modified gravity frameworks have been developed that improve agreement with cosmological data, but none has yet demonstrated the same comprehensive agreement with observations that the standard cold dark matter model achieves. The current scientific consensus is that MOND is a genuinely interesting empirical pattern at the scale of galaxy rotation curves, one that any successful dark matter theory needs to explain, but that it fails to replace dark matter at larger scales and within the framework of cosmological structure formation. For retention, MOND is important because it prevents the script from sounding like propaganda. The viewer should feel that the alternative has been taken seriously. Modified gravity is not a silly idea. At galaxy scales, it captures real patterns that dark matter models must explain. But when the story widens to clusters, lensing, the bullet cluster, the CMB, and cosmic structure, dark matter remains the more successful framework. This makes the conclusion stronger because it has survived a real competitor, not a straw man. The concordance cosmological model, incorporating cold dark matter, matches the full range of observations from CMB fluctuations to large-scale structure to galaxy cluster dynamics in a way that no pure MOND theory has achieved. This doesn't mean the MOND observations are uninformative. In fact, they may be telling us something important about galaxy formation. Perhaps ordinary matter and dark matter become tightly coupled through feedback. Gas cools, stars form, supernovae explode, gas flows outward, halos respond, and the final galaxy remembers the distribution of baryons in a surprisingly regular way. Perhaps simulations still miss some subtle physics of how galaxies assemble. Or perhaps the empirical relations are pointing toward a deeper law not yet understood. This keeps the debate scientifically alive without making the conclusion vague. The standard dark matter model wins on the full range of evidence, but galaxy-scale regularities remain a clue. The tight empirical relations between visible and dark matter at galaxy scales, the radial acceleration relation, the baryonic Tully-Fisher relation, may be telling us something important about how dark matter halos form and how they couple to the distribution of ordinary matter, or possibly about fundamental aspects of gravity not captured in the simplest dark matter model. They remain active areas of theoretical and observational investigation. The role of dark matter in cosmic structure formation is so central to our understanding of the universe that it deserves its own careful consideration, independent of the rotation curve and cluster dynamics evidence. The large-scale structure of the observable universe, the cosmic web of filaments, sheets, voids, and clusters that we observe in galaxy surveys, grew from the tiny density fluctuations present in the early universe, the same fluctuations visible in the CMB. The cosmic web is the largest scale version of the same story. On small scales, dark matter holds galaxies in halos. On cluster scales, it supplies most of the mass. On cosmic scales, it forms the invisible skeleton around which galaxies arrange themselves. Galaxy surveys show filaments, walls, clusters, and voids. The luminous galaxies trace the structure, but they are not the whole structure. It is like seeing dew on a spiderweb in the morning. The droplets show the web's outline, but the web was there before the droplets made it visible. In the universe, galaxies are the shining droplets. Dark matter is much of the underlying web. The process of growth is gravitational instability. Slightly overdense regions attract more material, growing denser, while underdense regions lose material, becoming voids. Over the 13+ billion years of cosmic history, initial fluctuations of 1 part in 100,000 have grown into structures with density contrasts of millions to billions over their surroundings. The rate at which this growth occurs depends crucially on the composition of the universe. This is where dark matter becomes not only a hidden ingredient, but a timing solution. The universe we observe today has large structures, galaxies, clusters, filaments, and voids. But the early universe, as seen in the CMB, was very smooth. The fluctuations were tiny. There has to be enough time and enough gravitational growth to turn that smooth early state into the clumpy modern universe. Ordinary matter alone cannot do this efficiently enough because it was tied to radiation before recombination. Dark matter starts building the scaffolding earlier. Ordinary matter, baryons, the protons and neutrons of atoms, was tightly coupled to radiation in the early universe through electromagnetic interactions. This coupling prevented ordinary matter from collapsing under gravity before the universe became transparent, because the radiation pressure counteracted gravity. The baryon-photon fluid oscillated rather than collapsing, producing the acoustic oscillations visible in the CMB power spectrum and in the clustering of galaxies. Dark matter, by contrast, being electromagnetically non-interacting, was not coupled to radiation. Dark matter fluctuations could grow under gravity from a very early time, beginning well before recombination. By the time ordinary matter was released from its coupling to radiation, at the epoch of recombination, 380,000 years after the Big Bang, dark matter halos had already grown significantly, providing gravitational potential wells into which the newly freed ordinary matter could fall. This is one of the most beautiful parts of the story. Dark matter was already preparing the architecture before ordinary matter could fully collapse. When atoms finally formed and light could travel freely, baryonic matter began falling into gravitational wells that dark matter had helped create. The visible universe arrived late to a structure already under construction. That is why dark matter can be described as scaffolding. It is not the shining building. It is the hidden framework that made the building possible. The dark matter halos served as seeds for galaxy formation, guiding ordinary matter into the structures that would become galaxies. Without dark matter, ordinary matter would have had to grow all the large-scale structure we see from very small initial fluctuations in only 380,000 years before recombination, a time far too short for significant growth at the scales relevant for galaxies and clusters. The resulting matter-power spectrum, the distribution of structure across different scales, would be dramatically different from what is observed. The observed large-scale structure of the universe, as measured in the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and more recent surveys, matches the predictions of cold dark matter models with extraordinary precision. Modern surveys make this visible in a way earlier astronomers could not have imagined. Instead of one galaxy at a time, surveys map millions of galaxies, assigning them positions in three-dimensional space. The result is not a random spray. It is a cosmic web, filaments stretching between clusters, walls surrounding voids, knots where galaxies gather most densely. This pattern is one of the fingerprints of dark matter. The visible galaxies outline the structure, but the gravitational growth was dominated by something dark. The map itself becomes evidence. Removing dark matter from these models produces predictions that fail comprehensively to match the observations. Dark matter is not an add-on to the cosmological model. It is structurally necessary for the model to produce a universe that looks like the one we observe. This is the deepest reason the title works, even after we correct the word force. Dark matter does not hold the universe together like glue, but it does provide the gravitational scaffolding on which ordinary matter assembled. It shaped the places where galaxies could grow. It guided gas into halos. It allowed structure to develop early enough for the modern universe to exist in the form we see. It is invisible, but the visible universe grew inside its gravitational architecture. This is a different type of argument from the rotation curve evidence or the cluster dynamics evidence. It is not about the mass budget of specific objects, but about the dynamical history of the entire observable universe. The small-scale challenges to the cold dark matter model, sometimes called this small-scale crisis, are one of the most actively debated areas of current cosmological research, and they are scientifically important because they might point toward modifications of the simplest cold dark matter picture, or toward a new understanding of how ordinary matter processes modify dark matter's predictions. This section is important for viewer trust. A weaker script would present dark matter as if every detail is solved except the particle. A stronger script admits the real situation. The broad evidence is powerful, the cosmological model works remarkably well, and still there are small-scale tensions. Dwarf galaxies, satellite counts, central density profiles, and feedback physics are not boring details. They are where the clean model meets the messy universe of gas, stars, explosions, and observational limits. That honesty makes the mystery more credible. The missing satellites problem refers to the discrepancy between the large number of small dark matter subhalos predicted by cold dark matter simulations of galaxy-sized halos, typically several hundred to a few thousand subhalos that could in principle host small satellite galaxies, and the relatively modest number of satellite galaxies actually observed around galaxies like the Milky Way. The word missing can be misleading here. The simulations predict dark matter subhalos, not necessarily bright galaxies. A small halo may exist, but contain too little gas or too few stars to be easily seen. If reionization heated its gas, if supernovae expelled material, or if the halo never formed many stars, it could be present gravitationally while almost invisible optically. That means the problem is partly about dark matter and partly about the complicated question of when a dark matter halo becomes a visible galaxy. This is why new surveys matter. Finding ultra-faint dwarfs changes the count. Better simulations change the prediction. The crisis becomes a measurement of both dark matter and galaxy formation. Early cold dark matter simulations predicted more satellites than were observed by a factor of roughly 10 to 50. The resolution of the missing satellites problem now appears to largely lie in astrophysical processes rather than in modifications to dark matter physics. The ultraviolet radiation field from early galaxies, which reionized the intergalactic medium early in cosmic history, heated and expelled gas from small dark matter halos, preventing star formation in the smallest subhalos and leaving them as dark satellites, dark matter halos with little or no associated visible galaxies. Supernova feedback, the energetic outflows from exploding massive stars within small galaxies, can further expel gas from small galaxies, reducing their stellar mass below detectable thresholds. The combination of photoionization suppression and supernova feedback, implemented in increasingly sophisticated hydrodynamic simulations of galaxy formation, substantially reduces the predicted number of visible satellite galaxies to numbers more consistent with observations. Additionally, improved searches for ultra-faint dwarf galaxies using surveys like the Dark Energy Survey, the Pan-STARRS Survey, and the upcoming Vera Rubin Observatory are finding many more faint satellite galaxies than older, less sensitive surveys discovered, further reducing the observational deficit. The cusp core problem refers to the discrepancy between the dark matter density profiles predicted in the centers of small galaxies. Cold dark matter simulations predict steeply rising cuspy profiles, and the observationally inferred profiles of some dwarf and low surface brightness galaxies, which appear to show flatter, cored central densities. This is a subtle but important problem. A cusp means the density rises sharply toward the center. A core means the density flattens. The difference is not only a mathematical shape. It tells us about the history of energy moving through the galaxy. If repeated bursts of star formation push gas outward, the gravitational potential changes. Dark matter responds to those changes. Over time, this can transfer energy into the dark matter and soften the center. That means ordinary matter, though it is only a minority component, can reshape the visible consequences of dark matter. The same supernova feedback that reduces the satellite count can also address the cusp core problem. Repeated cycles of gas outflow and infall, driven by bursts of star formation and feedback, can transfer energy to the dark matter and gradually flatten the central cusp into a core. The effectiveness of this mechanism depends on the star formation history of the galaxy and the specific feedback prescriptions in the simulation, and current simulations with realistic feedback do produce cored profiles in some dwarf galaxies. The too big to fail problem. The observation that the most massive subhalos predicted around Milky Way-like galaxies are more massive than any of the Milky Way's classical dwarf satellites has similarly been substantially addressed by including the full range of baryonic physics in galaxy formation simulations, though debates about the precise severity of the problem and the adequacy of the proposed solutions continue. These small-scale challenges are not considered fatal to the cold dark matter model by most working cosmologists, but they motivate continued scrutiny of the assumptions in dark matter simulations and continued improvement in the observational characterization of small galaxy systems. The phrase "not fatal" should not make the small-scale problems sound unimportant. They are important because they may be where the identity of dark matter leaves subtle fingerprints. Two models can look almost identical on the scale of galaxy clusters and the CMB, but differ in the centers of dwarf galaxies or in the abundance of tiny halos. The smallest galaxies may therefore become laboratories for the deepest particle physics. Sometimes the answer to a cosmic question hides in the faintest systems. For the viewer, this gives the episode another reason to continue. The question is not simply yes or no dark matter. The more interesting question is what kind of dark matter and what kind of galaxy formation. Is dark matter perfectly cold and collisionless? Does it self-interact weakly? Is it warm enough to erase small structures? Is it wave-like at tiny masses? Or are the apparent tensions mostly the result of ordinary matter physics being harder to simulate than the dark matter itself? The answer will not only identify a particle, it will explain why small galaxies look the way they do. They also motivate interest in dark matter models, self-interacting dark matter, warm dark matter, fuzzy dark matter, that might naturally produce chord profiles and reduce the excess of small subhalos. The future of dark matter research over the coming decade involves multiple parallel programs, each attacking different aspects of the problem from different directions. This multi-front search helps the episode end with momentum. If the story were only that experiments failed, it would feel discouraging. But the actual situation is more active. Old candidate spaces are closing. New ones are opening. Detectors are becoming sensitive to neutrino backgrounds. Surveys are mapping weak lensing at enormous scale. The Vera Rubin Observatory and Euclid are now reshaping survey cosmology. Axion experiments are improving. Gravitational waves are adding another way to test compact dark candidates. The silence so far is not the end of the search. It is the sharpening of it. This is where the story opens forward. A mystery can feel frustrating if it has no path toward resolution. Dark matter does have paths. They are difficult, expensive, and technically demanding, but they are real. Underground detectors are listening for nuclear recoils. Axion experiments are tuning through possible masses. Galaxy surveys are mapping the cosmic web. Gravitational lensing is measuring invisible mass. Dwarf galaxy studies are testing small-scale structure. Particle colliders are looking for missing energy. Gravitational wave observatories may constrain primordial black holes. The search is not one experiment waiting alone in the dark. It is a network of attempts surrounding the mystery from every side. The Vera Rubin Observatory, through the Legacy Survey of Space and Time, has begun the most comprehensive optical survey of the southern sky ever undertaken, photographing roughly 20 billion galaxies over 10 years and building up a dataset that will be used for weak gravitational lensing maps of the dark matter distribution, searches for faint satellite galaxies and stellar streams around nearby galaxies, detection of new Milky Way satellites, and measurement of the dark matter halo, profiles of nearby dwarf galaxies through stellar kinematic studies. Rubin is especially important for the small-scale story. If missing satellites are hiding as ultra-faint dwarf galaxies, Rubin is one of the instruments most likely to find more of them. If stellar streams around the Milky Way have been disturbed by invisible dark matter subhalos, Rubin's deep repeated imaging may help reveal those disturbances. If the shape of the dark matter halo influences how stars move in the outskirts of galaxies, long-term surveys can map the clues. This is not only a survey of things that shine. It is a survey of how shining things have been shaped by what does not. The Euclid Space Telescope, launched in July 2023, is a European Space Agency survey mission conducting wide-field optical and infrared imaging and spectroscopy of huge numbers of galaxies. Its first survey data release in 2025 already contained tens of millions of galaxy detections, a small preview of the larger map to come, specifically designed to measure dark matter and dark energy through gravitational lensing and galaxy clustering measurements with unprecedented statistical power. Euclid attacks the problem from the geometry of the universe. By measuring galaxy shapes and positions over a huge volume of space, it can trace how matter is distributed and how structure has grown over time. Weak lensing tells where mass lies. Galaxy clustering tells how matter has assembled. Together, they help test the dark matter framework and the dark energy-driven expansion history in one enormous survey. The name Euclid is appropriate. The mission is about cosmic geometry. The DESI spectroscopic survey at the Kitt Peak National Observatory in Arizona is measuring the three-dimensional positions of tens of millions of galaxies, mapping the baryon acoustic oscillation signal and the matter power spectrum across a vast cosmic volume, providing constraints on dark matter's properties from large-scale structure that complement the lensing and kinematic measurements. DESI adds distance precision. Images show where galaxies appear on the sky. Spectra show how much their light has been redshifted, allowing astronomers to place them in three-dimensional cosmic maps. With enough galaxies, the pattern of clustering becomes a ruler left over from sound waves in the early universe. That ruler helps measure cosmic expansion and the growth of structure. Dark matter appears here not as a particle in a detector, but as a pattern in the arrangement of galaxies. The next generation of direct detection experiments, including the XLZD Consortium's planned multi-10-ton liquid xenon observatory, future Panda X upgrades, and other technologies, is designed to push WIMP sensitivity toward the neutrino fog and to develop new methods that may help separate a possible dark matter signal from neutrino backgrounds. The future of direct detection will therefore become more subtle. Bigger detectors help, but size is not enough. Backgrounds must be understood at extraordinary precision. Neutrinos must be modeled. Directional information may become crucial because a dark matter signal should appear to come from a preferred direction related to the solar system's motion through the galactic halo, while many backgrounds should not. If future detectors can measure recoil directions, they may separate a dark matter wind from the neutrino fog. The search becomes not only bigger, but smarter. The next step will also be more interdisciplinary. A future signal will not be believed because one detector sees one unusual event. It will need consistency, energy spectrum, timing, direction if available, absence of known backgrounds, agreement with other experiments, and compatibility with astrophysical constraints. Dark matter is too important for a weak claim. The first detection, if it comes, will be examined with extraordinary suspicion before it becomes accepted. The proposed IAXO axion helioscope, a large next-generation facility concept using a long superconducting magnet with X-ray optics, aimed at the Sun to detect solar axions through their conversion to X-ray photons in the magnet, would extend axion search sensitivity to couplings orders of magnitude below current laboratory limits. Axion searches also have more than one strategy. Some experiments look for dark matter axions in the galactic halo. Others look for axions produced in the Sun. Still others use laboratory light shining through wall experiments, precision magnetometry, or astrophysical constraints. This diversity matters because the axion, if it exists, may sit in a mass and coupling range that only one technique can reach. The search is like exploring a dark coastline with many kinds of lamps. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector currently under development by ESA for launch in the 2030s, is expected to detect gravitational waves at lower frequencies than ground-based detectors, including signals from massive black hole mergers and perhaps backgrounds or populations relevant to early universe physics. Depending on what nature provides, such data could help constrain primordial black holes and other dark sector ideas. Gravitational waves widen the dark matter search in a different direction. If some fraction of dark matter is connected to primordial black holes, phase transitions in the early universe, cosmic strings, or other exotic relics, the clue may not be a particle recoil or a photon signal. It may be a vibration in space-time. This is one reason the dark matter problem now belongs to multi-messenger astronomy. Light, gravity, particles, and cosmic structure all become possible witnesses. The unknown is large enough that no single method should be trusted alone. Each of these programs could produce a detection that transforms our understanding of dark matter, or could continue to find nothing and tighten the constraints further, or, perhaps most valuably, could find something unexpected that doesn't fit any of the current candidate categories. The most exciting possibility may not be that one favorite candidate wins cleanly. It may be that the universe does something stranger. A signal could appear in an axion experiment at an unexpected mass. A direct detection experiment could see an annual modulation or recoil spectrum that does not fit a simple WIMP. A survey could find small-scale structure inconsistent with cold dark matter. A gravitational wave population could reopen a primordial black hole window. Or all of these searches could remain silent long enough that theorists are forced into a new framework. The history of science often turns on the result that was not on the first list of expectations. The history of physics suggests that the most important discoveries are often the ones that don't fit neatly into existing frameworks. Let's close by sitting with the genuine strangeness of the situation we are in. By this point in the episode, the viewer has earned the final reflection. We began with a simple idea. The universe contains more matter than we can see. But that idea has now passed through galaxies, clusters, ancient light, particle detectors, modified gravity, dwarf galaxies, and future surveys. The mystery has become larger, not smaller, because the evidence is strong and the identity remains absent. That is the right emotional shape for this topic. The ending should not pretend to solve dark matter. It should let the viewer feel the weight of a real, unsolved problem. 85% of all the matter in the universe is made of something we have never detected directly. This is the sentence that should remain with the listener, not because the exact percentage is the only important fact, but because it reverses ordinary intuition. We live among atoms. We touch atoms, breathe atoms, eat atoms, build with atoms, and see by the light atoms emit or reflect. Yet atoms are not the dominant matter component of the universe. The familiar kind of matter is the exception, not the rule. That is a profound displacement of human intuition. In earlier centuries, astronomy displaced Earth from the center of the universe. Later, it displaced the Sun from the center of the galaxy. Modern cosmology displaced the galaxy from any special cosmic location. Dark matter adds another displacement. Even the kind of matter we are made from is not the main kind of matter. It is not made of atoms. It is not made of any particle known to physics. It does not emit or absorb light. It does not respond to electromagnetic fields. It exists in an enormous halo surrounding our galaxy, a halo that extends for hundreds of thousands of light years, and it passes through the Earth continuously at several hundred kilometers per second, without interacting with any detector we have built. It has been responsible for much of what the universe looks like. This is why dark matter is not merely hidden. Something can be hidden and irrelevant. Dark matter is hidden and formative. It helped determine where galaxies formed, how clusters grew, how filaments connected, how ordinary gas found gravitational wells deep enough to collapse, and how the universe moved from near smoothness to structure. Its invisibility makes it mysterious. Its influence makes it central. The visible universe is not separate from the dark one. It is built inside it. This is why the episode can stay calm without becoming flat. The idea is enormous, but it does not need theatrical language. Every ordinary astronomical image already contains the implication. A spiral galaxy is not only a spiral of stars. A cluster is not only a cluster of galaxies. A deep field is not only light from the past. Each visible structure is also a sign of an invisible mass distribution that helped place it there. The viewer can keep returning to that image, light arranged by darkness. Without it, galaxies would not have formed in the way they did. Without it, the large-scale structure of the cosmic web would not exist in its current form. Without dark matter's gravitational wells providing seeds for galaxy formation, the ordinary matter of atoms and molecules would not have had the structure it needed to assemble into the galaxies, stars, and planets that produced us. In the most literal sense, dark matter made it possible for you to be here, not through any direct interaction with the carbon and oxygen and hydrogen of your body, but through the gravitational scaffolding it provided for the structures in which stars formed and planets assembled and life evolved. The universe is mostly made of something we know almost nothing about. There is humility in that sentence, but also excitement. Modern science has mapped galaxies across billions of light years, measured the age of the universe, detected gravitational waves, imaged black hole shadows, landed probes on other worlds, and read the chemistry of exoplanet atmospheres. And still, most matter remains unidentified. This is not a sign that science has failed. It is a sign that science has reached the edge of something real. The edge is where the next story begins. We have measured it from a great distance, through its gravitational effects, and what we see is that it is real, it is ubiquitous, and it does not respond to any of the tools we have most naturally developed for studying matter, which are all, ultimately, electromagnetic. We are electromagnetic beings, living in electromagnetic structures, using electromagnetic instruments, and the dominant form of matter in our universe is something that exists entirely outside the electromagnetic world. This is perhaps the most humbling part. Our senses evolved around electromagnetism. Sight is electromagnetic. Touch is electromagnetic. Chemistry is electromagnetic. Most instruments extend those same interactions. Cameras, radio telescopes, X-ray detectors, infrared sensors, spectrographs. We are extraordinarily good at studying what light and charge can reveal. Dark matter refuses that whole language. So we study it through gravity, the one language it appears to share. That is a strange and humbling situation. And it is also, from the perspective of anyone curious about the fundamental nature of things, one of the most exciting situations in the history of science. Something real and vast and completely unknown is waiting to be understood. That is the emotional center of the episode. Dark matter is not simply a gap. It is a presence. A gap is something missing from a theory. Dark matter is something whose gravity is already written into the motion of galaxies and the pattern of the cosmic web. It is unknown not because it is optional, but because it has so far stayed outside the kinds of interactions our instruments can easily use. The search goes on, in the deep rock mines where liquid xenon sits quietly waiting for a collision, in the microwave cavities where magnetic fields are tuned to whisper frequencies that might reveal an axion, in the telescope data where the shapes of billions of galaxies contain the faint signature of curved space, in the simulations where cosmologists are testing whether any of the proposed candidates can reproduce everything we observe. Each search has a different kind of patience. The underground detector waits for a recoil. The axion cavity waits for a frequency. The survey telescope waits for enough galaxies to turn tiny distortions into a map. The simulation waits for assumptions to be tested against the real universe. None of these approaches is guaranteed to win, but together they make the mystery harder and harder to escape. The invisible is being surrounded. The answer is there, somewhere, in the data we have or the data we will collect. That sentence should feel hopeful, but not naive. The answer may not come from the next detector run. It may not come from the most popular model. It may arrive as a confusing anomaly that takes years to understand. It may come from a combination of small clues, a lensing pattern here, a dwarf galaxy structure there, a laboratory constraint somewhere else. Fundamental discoveries often look untidy before they become clear. But the reason for hope is real. Dark matter is not a mystery without handles. It has gravitational handles everywhere. And when the answer comes, it will change more than one field. If a detector finds a dark matter particle, particle physics will change. Cosmology will change. Galaxy formation will change. The standard model will no longer be the complete list of matter's basic ingredients. The invisible scaffolding of the universe will have a name, a mass, and an interaction, however faint. If the answer comes instead through modified gravity or a more complex dark sector, the change may be even deeper. Either way, dark matter is not a minor loose end. It is a doorway into the next version of fundamental physics. Wherever you are right now, in a room, in a bed, with the lights low, dark matter is moving through you. This final image works because it brings the cosmic back to the room. The episode began with galaxies and the universe's missing mass. It ends with the idea that the mystery is not only far away. If dark matter forms a halo around the Milky Way, then the solar system is moving through it. The Earth is moving through it. The detector underground is moving through it. The listener is moving through it. The unknown is not at the edge of the universe. It is part of the environment we inhabit. That makes the mystery intimate in a way few cosmic mysteries are. The cosmic microwave background is ancient and distant in time. The first galaxies are far away. Black holes may be remote. But the local dark matter halo is here, in the same region of the Milky Way as the Sun. If dark matter is particulate, the particles do not need to cross intergalactic space to reach us. They are already part of the galactic environment through which Earth moves. The universe's missing matter is not only out there. It is around us. This image should be handled carefully. It depends on particle models that have not yet been confirmed. We do not know that dark matter is made of particles passing through your body in exactly the way a WIMP model imagines. It could be axion-like. It could be something stranger. It could be a dark sector with more structure than we expect. But if the broad halo picture is right, then Earth is moving through a local dark matter density, and any particle form of dark matter would be present around and through us. That is the strange intimacy of the mystery. Dark matter is cosmic, but not distant. Hundreds of billions of particles per second, if the most popular models are right. They carry no message you can receive, exert no force you can feel, leave no trace in any detector yet built. But they are there, part of the invisible structure of a universe that is, even in its most familiar feeling corners, stranger and more surprising than it seems. That final uncertainty is honest. If the particle picture is right, dark matter may be passing through you now. If the axion picture is right, the local halo may behave more like a field than a stream of little bullets. If the answer is a richer dark sector, the truth may be stranger than either image. The details are unknown. The gravitational fact remains. The Milky Way is not held together by visible matter alone. The familiar night sky is embedded in an invisible mass distribution. That is enough mystery for one quiet ending. The universe is not only what shines. Sometimes, what cannot be seen is what gives the shining things their place. That is the calm final shape of the episode. The listener does not need to leave with a particle name. No one has that name yet. The listener should leave with a clearer picture of the situation. Dark matter is not a fantasy, not a vague darkness, not a decorative mystery added to astronomy. It is a gravitationally measured component of the universe, supported by evidence from many scales, and still physically unidentified. That is enough to make the darkness feel real without making it supernatural. That is the final idea the viewer should carry away. The visible universe is not less beautiful because it depends on the invisible. It is more beautiful because the shining parts are embedded in a structure deeper than light. Every galaxy image, every cluster, every filament of the cosmic web is also an image of something unseen, inferred through gravity, waiting for a physical name. Dark matter is the reminder that the universe can be measured before it is understood. It can be mapped before it is named. It can shape everything while remaining almost completely silent. That final silence is not emptiness. It is the silence of something that does not use the channels we are used to listening through. No spectral line, no reflected light, no ordinary collision, no obvious track. Only gravity, repeated again and again, from the edge of a galaxy to the first light of the universe. That is why the ending should stay calm rather than dramatic. The mystery is already large enough. Good night.